Hello students, welcome to the digital learning of session 3 of unit groups of BSc 3rd Sem Mathematics. I am Dr. Shashikala. In this session 3, let us discuss about definition and properties of subgroup. Explanation of the semigroup. A non-empty set G with binary operation star is called a semigroup. Then it should satisfy the two laws here. One is closure law, another one is the associative law. So here, so semigroup example for the semigroup is natural numbers, set of natural number with the operation of addition, set of integers under the operation the multiplication. Then for the example of abelian group, we can take it as z comma plus q, that is the set of rational numbers with the operation addition, set of real numbers with the operation addition, set of complex numbers with the set of addition. This are all as an example of the abelian group. So example definition of the subgroup. A non-empty set H of a group G is said to be a subgroup of the group G if H is a group under the same binary operation of the G. That means if H itself is a group here, that means as we know group should satisfy the four laws. One is closure, associative, the identity existence, and the existence of the inverse. If it is satisfying, any element is satisfying, then we will say that as a G or group. So similarly, if H is satisfying all these axioms, then we can also say that it is a group only. Therefore, a non-empty subset H of a group G comma star is said to be a subgroup if H comma star is itself is a group. Example for this is one set of 1 comma minus 1 under the multiplication operation is a group of the subgroup of G is equal to 1 minus 1 I and minus I under the operation multiplication. So another subgroup example is Z comma plus is a subgroup of the integers rational numbers, set of rational numbers with the addition, operation addition. Set of rational number with the addition is a subgroup of the real number with the addition. Real number with the operation addition is a subgroup of the complex number with the operation addition. So next, the important concept is necessary and sufficient condition for a subgroup. Statement is a non-empty subset H of a G is a subgroup of G if and only if for all AB belongs to H, then A star B belongs to H. Then second is for all A belongs to H, A inverse belongs to H. We have to prove it for these two conditions. And remember that it is a if and only if condition. That means it's like a non-empty subset H of a group G is subgroup of G means taking this we have to prove it for first and second condition. Then secondly, taking first and second condition we have to prove it for H is a subgroup. So firstly go for a necessary condition, that is taking suppose H is a subgroup of G, then H is a group, therefore H is, remember that H is a group here or H is a subgroup, therefore automatically it is satisfying the two laws, that is the closure and the inverse law. What is that closure law says? For all AB belongs to H, A star B belongs to H. The inverse law is if taking element A which is belonging to H, then A inverse belonging to H. Then sufficient conditions. So this is for the necessary conditions. Sufficient condition means taking H which is subset of the G with A star B belongs to H, for all AB belongs to H, then A inverse belongs to H for all A belongs to H. Therefore, the closure and the inverse, that is A star B is for closure. Then we are considering A inverse which is belonging to H. So this is satisfying with the inverse law. So these two laws are satisfied under the sufficient condition. So which is true in H. Nextly, associative law. So two conditions is already proved. which are the two conditions, that is closure law and the inverse laws are proved. So another two conditions we are left with is associative law and the identity law. How to prove for associative law? As we have said, we have to consider three elements A, B, C here. So which implies ABC belongs to G. If ABC is belonging to H, again belonging to G means again it is belonging to H, because H is a subset of G. Therefore, ABC, for all ABC belongs to H, which implies A star of B star C is equal to A star of B of star C. So bracket, associative law means bracket, right? So therefore, bracket is for B and C. In the LHS side, again in the RHS side, bracket is for A and B. So again I am repeating here, the star means we can take the operation of addition and multiplication. Therefore, associative law holds. Nextly is for the identity law. So let's take A belongs to H, then A inverse belongs to H. Then, so taking A star of A inverse which is belonging to H, according to identity law, A and A inverse becomes E here. Therefore, E belongs to H, therefore identity law is satisfied. Therefore, H comma star is a group, therefore H comma star is a subgroup of the G. Then, property of the subgroup. Theorem. If H is any subgroup of a group G, then prove that product of any two subgroup is always a subgroup. So to prove this, let's take the two elements H1 and H2, which is a element of the H, and H is a subgroup of G. Then such that H1 and H2 belong to H, also H1 and H2 belonging to H. Therefore, so we have to concentrate on the small h and the capital H here. So we are having, or we are considering a two elements of the capital H, that is H1 and H2. So remember that H1 and H2 is belonging to H. Therefore, we are taking capital H into capital H, which is a subset of the capital H only. Call this as a equation number 1. Then, so identity element is taken here, that is E be the identity element of the G. Then H, what we have taken the one element H1. So for this, consider identity element E here, therefore HE, which is belonging to H into H. For all H belongs to H, and also for all E belongs to H. Therefore, H is subset of H into H. Therefore, call this as equation number 2. From equation number 1 and 2, H is equal to, because in equation number 1, in the RHS side we have a H. In the equation number 2, we have a LHS side. So in equation number 1, H is acting as a set. In equation number 2, H is acting as a subset. Therefore, H is equal to H into H. Therefore, product of two subgroups is again a subgroup of a group G. So theorem 2. So intersection of any two subgroup of a group is again a subgroup. For this, let's take two elements H1 and H2 be any two subgroup of G. So since we are proving for intersection here, intersection is taking for two elements H1 and H2, which is not equal to the pi, that is null set. Since E is an identity element present in both the subgroups, let's take A belongs to H1 and A belongs to H2. Therefore, A is belonging to H1 intersection H2. Then again take another element as a B. B belongs to H1 and B belongs to H2. Therefore, B belongs to H1 intersection H2. Remember that two elements we are considering A and the B, which is again belonging to H1 intersection H2. So we have H1 and H2 are the subgroups. Therefore, A belongs to H1 and B belongs to H2, which implies A is belonging to H1 and H2. So B we are taking for a inverse here. Therefore, A B inverse belongs to H1. Then again, A belongs to H2, B belongs to H2. Similarly, AB inverse belongs to H2. Therefore, AB is belonging to H1 and AB is belonging to H2 also. Therefore, AB inverse belonging to H1 intersection H2. Therefore, it is proved that H1 intersection H2 is a subgroup of a G. So, again we can prove it for the third theorem. A non-empty set H of a group G is a subgroup of G if and only if AB belongs to H, AB inverse belongs to H and B inverse belongs to G. Then, so if next theorem is, if A and B are any two elements of a group G comma star, then prove that A star B inverse is equal to B inverse star A inverse. So let G comma star be a group for all AB belongs to G and E is an identity element of G comma star. So we have to prove it for what? A star B of inverse is equal to B inverse star A inverse. Let's consider A star B of star of B inverse star A inverse. So let's change the bracket here for A star of B inverse star A inverse. Then again, according to the associative law, bracket is changed for B and B inverse. Then B and B inverse means, as we know, it is a E identity element. Therefore, A star of E star A inverse. Next is A inverse is with the E. Therefore, we are having only a A inverse. So, A star of A inverse is nothing but E. Call it as a equation number 1. So, similarly, we'll take for B inverse star A inverse star of A star B. So, firstly, to prove it for equation number 1, we have taken A star B star of B inverse star A inverse. Nextly, to prove it for equation 2, we are reversing it. That is B inverse star A inverse star of A star B. So taking again associative law property, changing of the brackets. So that is B inverse star of, bracket is for A inverse star of A star B. So again bracket is for A inverse star A. So what happens? A inverse star A becomes a E here. Therefore B inverse star of E star B. Therefore P is with the E. Therefore B inverse star B. So again B star of B inverse, that is B into 1 by B, it is like, which is nothing but a identity element E. Therefore equation number 1 is A star A inverse is equal to E. Equation number 2 is B inverse star B is equal to E. Therefore from equation number 1 and 2 we have got it as A star B inverse is equal to B inverse star A inverse.